Good morning, everyone. Welcome to our PC4 lecture. We started to discuss yesterday the chemical bond. In particular, in the context of the virial theorem, we can analyze a little bit further the distribution of the total energy, as you know it from the archetypical binding curves, among the potential energy and the kinetic energy contributions. So this kind of partitioning constitutes the first order sort of level of a deeper understanding of the chemical bond in terms of energies and physically meaningful quantities. Now, we distinguished 4 regimes, and I'd like to use the drawing we started yesterday. So we have this is an energy axis, right? So this carries units of whatever energy you wish. And if we say it comes in units of, let's say, U, right? Then we would be exactly at, well, let me put minus U. So then we have 1 U here, 2, 3. And these, sorry, nonsense, minus 1 here. These levels are related to each other. This is something, let me clean some space here. This is something which we obtained yesterday, that we have relationships between these offsets. So this relationship here is the kinetic energy at infinite distance. We showed yesterday that this is exactly the height of the total energy at the distance being also infinity between the atoms. So this is just the opposite sign, right? So this is minus U at R infinity. And we also saw that this is the same as minus 2 times V tot, right, at infinity. And so this is, of course, what you then see as you go from here to here. This is V tot at infinity. So the potential energy of your system at infinite distance is twice the energy of the total energy of the dissociated system, and half the opposite sign of the kinetic energy, right? So obviously at any point here, our U curve has to meet the condition that it sums up to these 2 contributions, right? All right. Now we distinguish these 4 regimes, and I'd like to draw them in here, just so this is. Oh, excuse me. So this is our R, and actually, this is the region, the long range region. This is our binding curve, U. This is U. This is T. And we have the something like that. So we have this interesting intermediate range. Oh, I'm sorry again. This is not the long range. This is the dissociated regime. And this is the long range. This is the bound case. And this is the short range. Yeah. So this is the graphical illustration of what we found yesterday. Now, in this long range, we saw that your kinetic energy should correspond to -5 C6 over R to the 6. And at the same time, for the potential energy, you would find +4 C6 over R to the 6, right? And so you add these two up and you get an attractive -C6 R to the 6. That's the leftover for your total energy, right? All right. Now, in the equilibrium case, where you have a total energy at the equilibrium distance, right? Which consists of the total energy of your free atoms plus the dissociation energy. At this point, you have your kinetic energy to be the same amount, but of opposite sign, okay? So this is T at RE equals U minus U at RE, right? And at the same time, you have then, by necessity, that this kinetic energy is the same as, again, the dissociation energy plus your kinetic energy at infinity. Likewise, for the potential energy, you will find that V tot at the equilibrium distance is 2 times U, the equilibrium distance, right? We also note that the difference from the free limit, so the free atom limit, corresponds to 2 times the dissociation limit. So in terms of potential energy, right, your electrons profit tremendously from the overlap, but you have to pay for it with some loss in kinetic energy. So as we talked about it, right, the curvature will grow in your binding scenarios, and so that makes your kinetic contribution less favorable. We also saw yesterday that we have some inequalities, right? So your potential energy, and this is obvious from the second line, must be much below. It should be subtracted to the. So this is below your infinite guy, and likewise for your kinetic energy, you're above the dissociated limit. So this is the bound case, right? The bound regime. And now you have in the short range, you have the parabola, the flip parabola we discussed yesterday. So this is the offset, right? So this value here is T at I equals 0. And the regime here tells you that the T function goes as minus 3AR squared. Now, in the electronic part, you see here the kinetic part diverging. So this is the alpha C beta over the distance, right? Diverges at R as R goes to 0. But if you subtract the divergent part, you would recover so this is the tot which corresponds to, this is V of the two nuclei fused. So this is the V of Z equals Z alpha plus Z beta. It's the united atom V. All right, so that would be this V. Plus, again, a parabola, namely 4a r to the 2. And now we subtract the diverging phase. Right. So that would correspond to, that would correspond to this dotted curve here. Okay. So what you see now is these two competing components, right? That contribute and that result in this archetypical binding shape. Now we should point out two non-trivial things, right? T and V are not monotonic functions in the distance. Rather, you have here a little minimum and here a little maximum. And so we can now discuss a little bit how they come about, and we can interpret this. So that's what we would still like to do now. So let's start by discussing behavior of your potential energy as a function of R. Right? So we start out with large R, starting with large R. The two potentials are so far away, and so let's suppose these are the two potentials, and this is R again, and so one nucleus sits here, the other one sits here. They are happy with their electrons, right? So you have some electron bound here. Let's put some wave function, and here's some wave function, but there's zero overlap. They're just too far away. Okay. So this is the offset, right? There's no overlap, and basically meaning that there's no interaction. So this is where we start from, right? This is the dissociated regime. And now, sorry, it's just some axes, this here, the distance R. Right? Now, as you reduce R, and you get into the long range regime, what you have is that the electrons, in terms of long range, they start to repel each other. These are negatively charged particles, most and foremost. So when you are at some small distance, but not too small, you still have your potentials, of course, and your electrons. They don't overlap, but there is interaction. Okay. And this would be, to first order, a classical Coulomb repulsion, right, of these electrons, right? So here, of course, you have your protons with your nuclear charges, right? They would attract each other's electrons, but first you get, at an even shorter distance, you have electron-electron repelling each other. So that kicks in before the protons of the nucleus start interacting. And this results, so there's a repulsive interaction. And this is what causes this little bump in the potential energy. Causes small local maximum in the potential energy. Okay. Now we go to the bonding regime, right? This is where you have the case that your potential now is close enough so that the electrons start to overlap. Right? And this is where you get a very deep attraction. Right? And then finally, as you push things further, right, into the short range, you see what happens to your potential. Now, all the electrons have to live in something which looks like a one big potential, right? So the intermediate part is down here. And both electrons, the electrons from both atoms, get squeezed together more than they would like to. And so this, and also, of course, the protons, right, get closer more than you would like to. And so this results in the divergent term. Right? So the electrons, right, as we discussed here, if it was only about the electrons, you would get this this part, but it's really then the nuclei which force the whole thing to take off, right? So electrons lose their increasing attraction, right? It levels off, you get this parabolic part. Nuclei start to repel. So this causes divergence. That's R towards 0. Okay. So this is basically the curve discussion of this V function, right? The potential. Now, in terms of kinetic energy, right? We can do a similar discussion. You also have the same limit. So regarding T, right? You can repeat discussion. The argument for the dissociated regime you can see above, right? It's the same as for the potential energy, so there's some constant. The argument for the long range regime is different, right? There's fundamentally a difference here. What you have is a local minimum, right? So the kinetic energy decays as you start interacting. Now it decays, the minimum is located closer to the equilibrium regime, right? So you have to think of, this is a little bit more like this, right? And this is here you have the result from the maximum for V. So this minimum region in the kinetic energy you could interpret as something. This is the regime which, as you transition to bound, right? Let's say in between long and bound range, or we go from long to bound, right? A regime in which smoothly the overlap gets turned on, which switches on overlap. Okay. So what happens, right? This means as you do this, right, the electrons delocalize, right? So you switch on this overlap, and as the first order effect at coming from the large distance, right? You slowly decrease the distance. It's the first order effect. Think about Heisenberg's uncertainty. Delta X times delta P, right? Larger equals constant, right? So delta X increases, right? That means delta X goes up, right? And your momenta must come down, which means your kinetic energy reduces. So that qualitatively explains this minimum as you slowly go from the long range into the bound range, right? Local minimum for T. And now as you approach the bounding region, right, your electrons start to, so it's basically your two nuclei here and your R, right? You're in this region where the the potentials are just overlapping sufficiently well so that your electrons just start to delocalize, okay? So then it flattens out, your electrons flatten out, you have less curvature. But then as you go smaller towards Re, as R to Re, right? Then again, your so this is Re. Then again, you now have good overlap, but the curvature, remember the shape of the electron density, the curvature has to account for the two nuclei, and so that results in your T growing rapidly again, right? So this is before you hit your equilibrium distance, right? You increase your T here due to the increasing curvature of the electrons in between your nuclei, right? So these are still two different regimes, right? And as you go from one to the other, you have a change in sign, right? If you wish, you change from attractive into repulsive. And then as your nuclei come closer, you get even more curvature, so it goes further up, right? So as E larger, R larger equals 0, your curvature grows, right? But it doesn't grow, right? As you remember this, so your potential as these two nuclei approach each other, and your potential in between drops further and further down. Your curvature grows, but it loses it grows increasingly less, leveling off in the limit of R going to 0, right? So your T converges towards the T at 0 distance. And from this perturbation expression, which we made use of without having derived it, but we just make use of this, we know that the rate with which it will level off corresponds to a flipped parabola. All right. So this is our view on the chemical bond in terms of the virial theory, which we derived together in the preceding sub chapter, and which rests on the hypervirial theorem, which is the expectation value of the commutator of our Hamiltonian with this linear operator A, which for the sake of these discussions, so for the virial theorem, we presume to be the product of momentum and position, right? So just think of Heisenberg, momentum and position. And we have seen unfold the distribution of, due to this additional relationship, right? we have this relationship that at any point in time your energy must be conserved, but you also have the virial relationship, and so that means we can rigorously and in a unique fashion partition the origins of these energy contributions. This I believe illustrates the power of quantum mechanics and the importance of the underlying formalism which we developed in chapter 2. Right? So the hypervirial theorem rests upon the properties of Hermitian operators, and so it was so important that we introduced this in chapter 2. Otherwise, you have no way to understand the virial theorem, and hence you have no way of tracking back the relative contributions stemming from potential or kinetic energy. So with this, I'd like to really switch gears now in this lecture series. We have discussed in the semester so far, after an introduction, we have discussed the theorems and postulates, so the formalism of the whole thing. We've introduced the variational theorem, which allows us to computationally converge approximate variance of Schrödinger's equation. We have covered perturbation theory, and now we have seen the applications of these concepts in the context of chemically obviously relevant questions, right? So we discovered we discussed the electron density as a simple observable, which due to the Ohn-Berg-Cohn theorem represents the wave function in a one-to-one map, right? So this is really really fundamental, right? Quantum mechanics is not something abstract. There is this electron density which you can measure and observe, and then we discuss its application to polarity, to dipole moments, and polarizability. So these are the most fundamental quantities in terms of Coulombic systems, right? So we're talking about electrostatics here. We have particles, matter is composed of particles with charges, our elementary particles, and so it's not surprising that these are the first things we should look at. And finally, we've used our framework to derive and to discuss the virial theorem, first in general, and then for the chemical bond as it is manifested in diatomics. So I hope you have gained some insights thanks to the discussions we've had so far. The second part of this lecture series will deal with more realistic discussion of more realistic applications of this underlying theory towards numerical simulations. Right nowadays, of course, computers are everywhere, and so we should discuss what we can obtain here. And in particular, we'd like to discuss as a next chapter. So next week, we will discuss Hückel theory, and I'm optimistic that we will also be able to discuss Hartree-Fock afterwards. as well as density functional theory. Depending on how quickly we proceed with these, we might also be able to briefly introduce correlated methods, as well as more technical points, such as basis sets, pseudopotentials, and possibly, I doubt we'll get there, but possibly, if we manage to get there, also what is known as model chemistry, which basically attempts to negotiate these two aspects of computational chemistry. Are there any questions regarding what we've covered now, or regarding the course?
Yes, just one thing, and that's the discussion about the curvature with the kinetic part.
Yes.
Could you just quickly recapitulate what you just said?
You mean this last part here?
Yes. Why does it grow exactly?
So you come out from we start out with the dissociated regime, right? So you have this offset here, right? Which by virtue of the virial theorem, we know this is repulsive, right? So this is the opposite of the total energy, right? Opposite sign. So this is where you come from R being approaching infinity, right? And then your atoms come together, right? And in this region where the electrons start to overlap, right? You have to realize that once, right before, at a larger distance, let me draw one larger distance here. Then for this distance, you would have a potential like this. Let me change color. So this is the dissociated regime. And so your electrons sit in here, right? And your electrons sit in these two guys, and they don't overlap, they don't see each other, right? So the potential, the space that's available to them is independent of the distance. But as they come so close that their potential here in between them allows the electrons to overlap, right? That is, to access the space of the other one. All of a sudden you have it, well, it's not all of a sudden, it's a continuous thing, but you suddenly get this, or you rapidly get access to this additional space for the electron. And that means your delocalization, your spatial accessibility must go up. And then by the uncertainty principle, right? This would imply that your momentum changes in momentum go down, and that so momentum is related to your kinetic energy, right? So that would mean that as your momentum go down, right, you lose kinetic energy, so you're going down in your T, and that is the reasoning for this local minimum in your T. That's what you have here, right? Does that make sense?
Yeah, I think so.
Okay. Yeah, and then the rest is that as you squeeze the atoms further together, then you need to get this binding curve, right? We discussed this, right, already. If you compare the electron density for the bound case, right, versus the free atom, right, then you see here there's a big change in curvature, and that means that your kinetic energy must go up again. All right. So I hope you enjoyed this first part. Next week, we will continue with Hücke theory and Hartree-Fock. And I have slides for this. There's less derivation to do. And so we will switch to presenting slides rather than doing everything by pen and paper. But on occasions, of course, if needed, we can always dial in the iPad and have a written discussion. So with this, I'd like to thank you for your attention, and I wish you a good end of the week still, and all the best, and I'll see you next Monday.